In this video, we are presenting our submission for the handover track of the 11th Robotic Grasping and Manipulation Competition, which was held on June 4th in the scope of ICRA2026 in Vienna. We are a student team affiliated with the University of Klagenfurt in Austria, led by Nadezhda Varsanova. The team is complemented by Daniel Bugelnik, Valerian Pichler, Christoph Rauter, and me, Markus Kreuter. The handover track consists of a natural human-to-robot handover in which the subject hands previously unknown objects to the robot arm, which should take them and place them back on the table without dropping or spilling their contents. The setup consists of a table on which the object is placed. The subject approaches the table from the opposite side of the robot and grasps the object, handing it over to the robot arm. We are using a UR7E robot arm together with a parallel jaw gripper on which our custom tactile sensors are mounted. A force torque sensor is used to detect touchdowns. As visual input, we use two Intel RealSense D435 cameras. All of the processing happens on our two workstations running Ubuntu 22.04 and ROS2 Humble. Here is what the setup at the competition venue looked like, giving you a good overview. Our system can be deployed within half an hour. After adjusting the robot workspace limits and static obstacles, we calibrate the cameras, for which we use an Aruco marker-based calibration board on the end effector. The calibration can be fine-tuned manually or automatically. To break down the perception pipeline, let's start with one camera. First, we are running our raw RGB data through a depth filter to isolate the workspace, after which we detect and segment objects using YOLO-E. MediaPipe is used to track the human hand and detect the handover start. The segmentation masks are projected onto the depth data to extract coordinates or to create a point cloud. In our solution, we use a dual camera setup. This spatial information of the hand and object is filtered and fused using a Kalman filter to estimate the object's 3D position. Let us take a look at the perception pipeline in action. Our position estimation runs at 30 frames per second. The handover starts when the subject reaches for the object. At this point, we produce a precise segmentation mask with SAM3 to get a segmented point cloud of the object. Using the GraspGen model, we generate potential grasp poses and filter them. The full pipeline consists of 3 stages with several steps. Firstly, the object's raw point cloud is filtered to reduce the noise, and a virtual proxy is reconstructed for symmetric containers based on visual clues. This step helps to generate grasps for poorly visible or noisy point clouds. Then, the generative model generates grasps symmetrically around the object's geometry, which are filtered out by geometric constraints. As soon as the object is grasped by the human, we filter out grasps that collide with the fingers. If we deal with an asymmetric container, and the container is reoriented around its z-axis, grasp replanning is initiated. The hand's voxelized representation is constructed using 2D hand landmarks from MediaPipe if available, otherwise a mask from SAM3 is used. Raycasting is used to check which grasp poses will collide with the fingers. The grasp is rejected if a ray intercepts the reconstructed hand's voxels. Here we demonstrate the grasping pipeline. After the object is taken, only valid grasps remain. The final grasp is selected via kinematic filtering, favoring the highest manipulability. For asymmetrical containers, the grasping pipeline replans the grasps if the object is rotated by a certain threshold, reusing the pre-generated grasps. The motion control module combines visual servoing, trajectory generation, and sensor-based interaction control. Motion is realized with Move-It2 servo, utilizing a PID controller for tracking, while a finite state machine controls the handover. A digital twin maintained within Move-It2 provides continuous collision checks. To reject outliers, object position estimates are filtered using a velocity gate and smoothed with a 1 euro filter. This graph illustrates our motion control pipeline. During the approach phase, the robot continuously tracks the predicted object position, adjusting the desired tracking distance dynamically as a function of object velocity. Grasping initiates upon object velocity stabilization and target distance convergence. To ensure reliability, the candidate grasps are evaluated against the robot's current configuration, and candidates that are near singularities are discarded. The best candidate is selected based on the robot's kinematics. For the sensor suite, we utilize our custom tactile sensors, which are highly sensitive and capable of detecting deformable objects. During closed-loop grasping, tactile measurements are preprocessed online and converted into binary contact events using a hysteresis threshold. For object placement, the wrist-mounted force torque sensor monitors the filtered force magnitude and detects the touchdown on the table surface. In closed-loop grasping execution, tactile events are monitored. The object is secured after both sensors detect contact. The position controller commands the gripper to close in discrete steps with exponential width partitioning. Our team achieved the highest overall score in the CourseMol benchmark amongst the teams participating this year. We had a 75.9% success rate across 288 configurations over all trials. In the live finals, we maintained a 75% success rate on unseen objects, even after a hardware failure disabled one of our tactile sensors. Additionally, post-qualification tuning allowed us to reduce our average handover time by over 30%, bringing it down to just 6 seconds, which spans the process from system start to gripper release. Finally, here are 3 handovers recorded during the competition. This work was funded by the Austrian Research Promotion Agency under the project ADAPTEX. We thank everyone involved for their invaluable support.